In today's discussion session, we will start discussing some other interesting states of quantum fields, and which would be handy when we discuss more interaction with atoms with different kind of classical or quantum fields. So in previous classes, we have learned about the structure of the vacuum of the field, vacuum state, how vacuum state is not completely empty, it comes up with correlations, and those correlations are have very nice structure of invariant distance determining the amount of correlation two particles could have. Now we will see whether this structure remains true for non-vacuum states or not, and in particular the non-vacuum state of a particular kind which is very close to a classical description goes by the name of the coherent state. There are thermal states as well, which we will discuss in the next class, but in today's class we will discuss about the coherent structure. Now, before going to coherent structure, what they are, if you are familiar with harmonic oscillator coherent structure, you should be able to sense the direction where we are headed to. So since we know for each momentum mode k, our description of the quantum field is that of a harmonic oscillator, therefore I can have the definition of a coherent state for that harmonic oscillator as well. So this tally very well with the discussions which you might have in the quantum mechanics course about the coherent state. The same kind of structure is present for the different K modes as well. Each one has its own coherent state. So we are going to list that state for particular mode K, its coherent state as alpha K, the ket alpha K. Okay, and this, as we know, is true because each different K is a separated harmonic oscillator structure. So now we know from harmonic oscillator analysis, a coherent state alpha is supposed to be eigenstate of the ladder operator A, the annihilation operator. And we know that our description which we are demanding is there is set of oscillators for each K. So therefore, in order to identify whose coherent state we are talking about, we put a label K. That means it is eigenstate of AK. And that eigenstate we are saying comes up with the eigenvalue alpha k. That's how we identify the state. The name alpha k ket is identified with their eigenvalue of the annihilation operator. As we know, annihilation operator is not Hermitian. A and A dagger are not the same thing. So therefore, this is not necessarily a real number. This can be a complex number. And these states, if you think, are not orthonormal states. And as if you are familiar with the literature of coherent state, you must be knowing that it is over complete basis rather than the complete basis. Okay. What we further know that these coherent states satisfy the Heisenberg uncertainty bound. That is, it is respecting this delta x delta p is equal to h bar by 2. So they are individual uh, variances in position in case of harmonic oscillators do come up with the minimum distributions individually they can come up with so that h bar by 2 is achieved. For instance, vacuum is also a coherent state which also satisfies this of a particular parameter. What about these alpha k's? These alpha k's are not bounded operators eigenspectrum, so therefore they are continuous variable and they are complex number. So I can have a complex number right now unbounded from anything. It is just possible complex number, and therefore I can have a coherent state of A eigenstate with different alpha which are continuous complex numbers. In position space, the A operator, annihilation operator, is a linear combination of x plus ip in a particular way. The same kind of a strategy will tell you how the field operators combination should be generating AK. Recall that the role of x is played by phi and the role of p is played by pi. And therefore, the same kind of decomposition which gives me the relation between x and p should give me the relation between the creation annihilation operators between phi and pi. All right. So still now we are just moving ahead on the structure which is already available at the level of standard quantum mechanics. So we are just copying that into the individual oscillator K. Also, again, I'm just quoting it from the quantum mechanical structure. If you want to write down the eigenstate of the creation annihilation operator rather A, that is the coherent state. That state can be written as exponential of alpha k times A dagger and alpha star times A exponentiated with some normalization constant. That acting on vacuum gives rise to this coherent state. Again, I am copying this from memory of quantum mechanics. You should go to quantum mechanics textbooks if you are unfamiliar with this and try to see how the eigenstates has this description. You can verify, given this alpha k, indeed this is true. So this is a good correct relation. And how this comes about, there are many ways of obtaining this around. You can go to any standard textbook of quantum mechanics harmonic oscillator and try to ask what is the representation of a coherent state in terms of some operators hitting the D. For instance, single particle excitation state is A dagger acting on 0. Two particles excitation is double A dagger with a factor 2 as well. With a factor 2, let us say, and so on. Okay, actually factor of root 2 should be. So if you keep hitting more and more A dagger, you will be getting more and more new states. Similarly, you can have a state where I have a twice this minus this is also a possible state, right? Two particles excited with some weightage alpha and one particle with weightage beta, and I take a minus sign. This is also a state, but this is written as in a particular way. This state is a double A dagger acting on vacuum, and this is a single A dagger acting on vacuum. So this is not a common operator which is hitting this. So you can write so many different states by combining how many excitations you want in which way to appear in the different components of superposition. One particular such distribution is this exponential. Exponential is identity plus this term plus the square of this term by 2 and so on. All those operators put together give you a transcendental series of states, excited vacuum state plus some coefficient times excited state plus some coefficient times second excited state and so on. And put together they constitute for you the coherent state. The exponential series, that transcendental series summing up to exponential of this kind gives you the coherent state. The same thing I write for the field momenta mode K's as well. And we have this thing where alpha k can take complex numbers. Now this is true for one oscillator set, and we have repeatedly said that the full description of the state is the collection of state from all possible oscillators. So therefore the full coherent state will be coherent state in each of the momenta mode. With what value, that will depend upon which alpha k function you choose. Each k, I have a different alpha value. So I have a alpha 1, alpha 2, alpha 3, alpha 4, so on. This is the full coherent state of this. What is alpha 1, alpha 2, alpha 3 individually is fixed by this alpha k number. So that's why a symbol k, subscript k was inserted. Alpha is a function of k. This is a function of k. So therefore, you would have a structure that coherent state of the full system is coherent state of individual things. And since vacuum is also a coherent state, one possible coherent state could be that alpha 1, alpha 2, then vacuum in 3, then vacuum in 5, and so on. So different values it is taking. For example, it could take value 1, this can take value 2, this is taking value 0. Alpha is equal to 0 as a vacuum state. This can take value 3 again. This can take value 0 again. So ultimately, if you plot as a function of k, you are getting 1, 2, 0, 2 again, or 3 again, and then 0 again. So this kind of plot for alpha k is coming about. Okay, so in principle, you can choose different functions alpha k, and you will generate resulting alpha, the full coherent state of the field. Okay, now given this coherent state of the field, we want to know what are the properties, expectations in the coherent state and correlations in the coherent state, whether they share the same structure like vacuum or not. In principle, we know they are not supposed to satisfy the nice structures of vacuum in a particular way, in the sense that if I compute even for one particle excited state, suppose I have a field in which only kth momenta is excited, all others are in vacuum, then also if you calculate phi x, phi y, then we do not get this to be equal to the vacuum 2-point function. So it will be different from the vacuum 2-point function. It is not equal to this. Actually, it is equal to this vacuum thing plus an additional thing, some function which depends upon which mode you have excited. So it's a function of k and x and y. This had a nice structure that it was 1 over d times minus 1 upon 4 pi squared. That was the invariant distance which were appearing. This will be some arbitrary function which will not be necessarily equal to any invariant quantity. So therefore, the coherent state also is not a vacuum state. So it is very rare to very non-trivial to think whether they will constitute additional f which is containing some usual geometric identities or not. So that is what we want to see. We want to compute for a particularly excited state like this and wish to know how different it is compared to the vacuum case. All right. So we go ahead and compute the expectation value of the field first. What we have to do, that is the standard exercise by now, we know how to compute expectations of field in various states. I will write down the decomposition of the operator phi in terms of a and a dagger, which is usual d3k upon root 2 omega integral with 1 over 2 pi to the power 3 by 2 factor outside. And inside I have plane wave times ak and plane wave star with ak dagger. That is the usual structure which we are familiar with. And as we know, compared to the vacuum case, which the same exercise we had done, this time we have to just do the alpha state will be squeezing AK and AK dagger as well. So the alpha state is squeezing. This will come with e to the power ik dot x and this will come with e to the power minus ik dot x. That's all it will happen. This alpha and this alpha squeeze operator this and this. All other things like are plane waves or integrals and other things. So they are not operators. Only operator that gets squeezed is this. Recall, uh, we are doing business only for scalar field for demonstration purpose. You can do the same thing for spinor field or vector field as well. So the operators which appear, squeeze operator which appear over here is AK, alpha and alpha AK dagger. This operator gets this operator this. Recall the alpha is supposed to be product of all k's and alpha k. So therefore, when I hit it with operator ak, let us say, let's call it k primed. This is integrated. This is product of all possible k prime. So when I hit with operator ak, it will search for its own momenta, and there will be one particular alpha at the same momenta k. This will be hit upon by this ak. All other states will be ignored by this ak operator. So ak acting upon alpha 1, alpha 2, alpha 3, so on, alpha k, then alpha n, all this thing. This operator will only identify this state. All other state it will go across and get up to this alpha k and hit it. When it hits it, since it is eigen state of ak operator, I will get a alpha k over here. Alpha k, ak back. Alpha k back. So there the squeezed thing is actually now converts itself into eigenvalue equation. So this becomes a number now from being an operator. So this will come out and therefore I will have an answer as alpha k and alpha k inner product. Since we had normalized the state, if you recall, we had put a normalization function over here. That means the state is properly normalized. So alpha k inner product is 1. I will be left with alpha k over here. So this becomes alpha k. You can argue this operator here gives you alpha k star times the bra alpha, and therefore bra alpha with ket alpha gives you 1 again. So you will realize after this action of the whole thing, the squeezing things of AK and AK dagger gives you alpha k and alpha k star with plane wave and plane wave star. So now we have obtained the expectation values as individually. We can just write it what these are in the open plane wave basis. So if I write down the ik dot x, I know there is a temporal part with a minus sign, which is e to the power minus I omega t, which I have separated, and the remaining thing, which is just complex conjugate of this, a plane wave with a complex conjugate of that. Okay, so overall, there is this d3k integral which is coming along, this d3k integral which is coming along, and there is a e to the power ik dot x which is here, and some function which I can call alpha k tilde. Together it is alpha k times e to the power minus I omega t. So this is some function overall. This looks like a Fourier transform of this function and its complex conjugate added. So depending upon what function alpha k you choose your business to start with, that means here I had a freedom to choose what alpha k, because these complex numbers just take any value from the complex space. So I can choose any alpha k to start my discussion with. That function multiplied with e to the power minus I omega kt divided by root 2 omega k. The whole thing will undergo Fourier transform, because everything depends on vector k. Omega k depends on vector k, and alpha k is also a function of k. So therefore, when I do the integration over d3k, I get a Fourier transform of my choice alpha k. So depending upon what function of alpha k you have chosen your alpha to be, you will get your expectation correspondingly. Expectation value will be the Fourier transform of your choice plus its complex conjugation. So therefore, anyone supplies you what is alpha k. For example, if I give you it is k to the power k times e to the power minus k, let us say, you will be able to do this Fourier transform, add its complex conjugate, and that will be your phi x. Okay. So therefore, this depends on your choice of what alpha k has gone. It is not a unique answer like a vacuum. Vacuum had a unique answer 0. This time it is non-zero. You can verify again. If I take alpha to be 0, this will be 0. Complex conjugate of 0 is also 0. So vacuum is a special coherent state where the choice of alphas are 0 for all k. Okay. If any of the alpha k is non-zero, then it is not vacuum state. So now your choice of your function alpha as a function of k will tell you what is the expectation of field in that state. What about its correlator? You do the game again. You obtain the phi x, phi y operator, squeeze it between the coherent state. So then the field phi is here, phi at x is here, phi at y is here with their individual integrations. The field phi comes with a k integrations, field phi at y comes with k primed integrations. And you write it down. Again, you will see there are 4 sets of operators. When alpha k goes with this alpha k primed, you will get this, which is squeezed between the coherent state. Then there is a possibility this alpha k goes with this alpha k dagger, k prime dagger, which is this, squeezed between the coherent state. Pay attention that when these first two combine here, the corresponding plane waves combine as a positive sign. When this alpha k goes and hits this ak dagger, I have a plus ik dot x and minus ik prime y. So the exponential function will change according to which of the operators you are trying to combine and what is their associated plane waves they are coming with. So first two terms give rise to this, this and this. The third term will be this combining with this alpha k dagger and alpha k primed. This time there will be minus sign in the plane wave of x, e to the power minus ikx, and plus sign is ik prime y. And lastly, this one combines with the last ak prime dagger, and you have exponential both with minus sign. So that is what the coherent state 2-point correlator structure will emerge out to be, and we will compute these things. Apparently, you can see that it is much different from the vacuum state. In vacuum state, many of these operators went away. Only one of the operators survived, which was the second number operator, right? Had it been 0, this would have annihilated it. Had it been 0, then the middle state would have survived, but all other states you can argue it would vanish. So now you can see on face of it, it is different from the vacuum, and how much different it is from the vacuum can be computed further. So you can find out what are the different operators appearing here. The 4 set of operators which are squeezed between alpha can also again be found from the information of a coherent state. Remember, ak acting on alpha will give me alpha k back with alpha. The two statements are true. Alpha k hitting alpha k will give me alpha k back with get alpha k as well. But this is true, and therefore the second line is also true for general alpha, which is the full coherent state of the full vacuum, to a full coherent state of the full field, because this is alpha 1, alpha 2, alpha k in between somewhere, then progress to some other alphas. So therefore, when AK hits it, it again goes and sees its own k momenta coherent state and k momenta coherent state, and then apply this information that it will get back the state with extra alpha k. That alpha k will come all the way out, and remaining thing is still the full coherent state. So you get this. Okay. So this is this. The AK will again hit the first AK primed hitting this alpha. The AK primed hitting this alpha has given me alpha k primed times alpha back. Then the second AK will again hit this alpha and give me AK hitting the second thing will hit this. AK will hit this. I will get alpha k primed and alpha k. So the first thing will become alpha k primed alpha k. The second thing has a dagger in between. So I have to do something to this. I do not know what is this. AK dagger hitting alpha k. I do not know what it is. So we have to do something about the middle term. The third term and the fourth term also have this structure. This is also going to give me alpha k primed times alpha, while this is going to give me alpha k star times get the bra alpha. Similarly, this will give me alpha k star bra alpha, and this will give me alpha k primed star get alpha. So all those things where we have wrote down. This quantity is going to give me this. Okay. Similarly, the third quantity will give me 1 alpha k star and alpha k primed, and the last quantity will give me alpha k star and alpha k star primed as well. What about the middle quantity which we had ignored? We can go back and use the commutation relation. We will flip again, like for quantum state, whatever we had done. We will flip this orders of AK and AK dagger using their commutator, which is delta function. So this AK dagger can be written as the delta of k minus k primed plus AK star AK dagger AK. So now this AK will go and hit this, give you alpha k, and this will hit this other side and give you alpha k prime star alpha k. So there will be an extra delta k minus k prime which will be earned by flipping this. So all those four terms now we have answer to. The first term is this much. The second term has two pieces, a delta and this term, and the third and four pieces have each one of them. So put it in the expressions which we wanted. In the previous slides, we have seen all the four expectations are coming with different exponential functions. So we take account of that and supply our non-zero values here, 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 and here. Again, you can cross check if alphas are put to zero, only this delta function term survives, everything else washes out. So now it is much more clear that it is different from the vacuum because there are surviving terms, non-zero surviving terms, which are contributing into the 2-point correlator. So what I do, I take this delta function, this will convert one of the k primed integrals into k integral and the usual vacuum structure. So the vacuum term I separate out. This is the delta function's contribution. Then there are remaining four terms, this, and that. And you can see they have very nice structure that they are individually made up from integral of this times integral of that. So this is cross product, or not cross, but direct product of two individual integrals. This integral and this integral put together generate all the four terms which are hiding here. And now we can identify these integrals. This is nothing but, if you remember, expectation of the field phi in the state alpha. So you see the extra term which we have generated are nothing but the individual expectation at x and individual expectation at y in the coherent state. So the 2-point function in the coherent state, call it g alpha xy, is vacuum 2-point function state and individual coherent state expectations. Okay. So now we have quantified how much different it is from the vacuum state. The vacuum state would have just given me gxy. This is the extra correction term due to presence of this alpha. So therefore, we can write down that the 2-point function minus individual expectation at location x and location y, their difference is equal to the vacuum 2-point function. In a classical system, if individual expectations are 0, individual numbers are 0 here and here, their product is also 0 classically. Quantum mechanically, as we argued, if expectation is 0, expectation is 0 here, that does not mean the product of these two operators have also 0 expectation. Now for coherent state, the difference between the product and the individual quantity is exactly the vacuum state. Okay. So it has almost a classical like a structure up to a vacuum. If I forget the vacuum piece, then this is what the classical thing would have done. The product is individual, the product expectation is individual expectations product. That is what a classical thing would have done. So coherent state is as good as a classical system up to an extra vacuum piece. So this 0 is the reminiscent quantum fluctuation of the vacuum. Okay, as we have repeatedly argued that vacuum state is just a particular realization of a coherent state. That coherent state class is a class which includes vacuum in it as well. So alpha is equal to 0 is the vacuum state. So for alpha is equal to 0, this vanishes, and therefore this becomes a trivial identity. Now this is for the field operator phi. What about its conjugate operator pi? Pi, if you recall, is a derivative of phi dot. So therefore it will throw up a minus I omega, because exponentials involve minus I omega t. If I search for a time derivative, it will just give me exponential back with this factor. And there will be a relative sign which will be coming about here, because both the terms do come with a different signs in the iota omega t. So this is the pi operator. Now you can compute the expectation of pi. Again, you will get that in vacuum, the pi's expectation is 0. In coherent state, pi's expectation is Fourier transform of a minus iota multiplied version of expectation of ak, which is you will get minus iota omega k divided by root 2 omega k times alpha k. That's Fourier transform. This will appear over here, and conjugate of that, this time with a minus. So previously it was a plus complex conjugate, this time it's a minus complex conjugate, because already we are talking about imaginary quantities. So far so good. So that is exactly the similar kind of thing, and therefore you will see that if I do the computation of 2-point correlator for conjugate field pi, everything else will fall through exactly like vacuum, exactly like the field phi description. Only thing, if you go back, if I did the business for the correlation in pi operator, what will just happen over here is, in this discussion piece which we had over here, things will only change with extra iota omega multiplications here and there and a sign difference. So for example, if we are looking at pi and pi over here, a minus sign should have come here, a minus sign should have come here, a minus iota omega k should have come from the first term, and minus iota omega k prime should have come from the second term. And you can see all the operators expectations will still go through the same: extra iota omega k, extra iota omega k primed, and a sign difference. First one plus minus minus plus. But operators in the computations which we are doing exactly remain the same kind of computations which we are doing. Even in the single pi expectation, if I did here pi expectation of alpha, only thing it might have happened, as we discussed, this will become a minus, and minus iota omega k will extra come out if I did. So you see, if I computed the 2-point correlator of pi, whatever we had done for phi almost goes through intact. Only relative sign difference and extra couple of omegas come about. But at the end of the day, exactly the same thing happens, that even the 2-point function of pi has the same structure as if that, sorry, as if that it is, so I have missed alpha here. It is a vacuum 2-point correlator of pi plus individual operator expectation of pi at location x and location y. So in my notes, if you are noting it down, just correct, there is a extra alpha alpha in between. So let me write it down. So there is a alpha here and a alpha here. So these are individual expectations. So 2-point correlator is vacuum plus individual expectation, just like the field expectation did. And this is true for any combination of operators. Phi and pi as well also do the same thing, that it is vacuum piece plus an extra individual expectation. So you see, coherent state are almost doing the classical thing. Classical things, any two operators product is equal to the product of their individual expectation. All the time we are getting an extra vacuum term. Apart from the vacuum part, it looks like that we are in a classical distribution. So coherent state is therefore somewhat of a vacuum added classical state. Okay, it is almost doing classical business, but with an extra reminiscent quantum effect in terms of this vacuum correlators. Okay, you can compute what is the number expectation operator. Number expectation is individual number operator in each mode and then sum over all possible modes. You can do this. You again work out the algebra as before. You will get the number operator is alpha k mod square integrated over all momentum modes. So that means alpha k mod square here is like a number density in per mode. And then you integrate over the whole volume over k, you will get total number. However, vacuum state, so unlike vacuum state, alpha is not an eigenstate of A dagger A, because A will convert it back into A. This will give me alpha k, A back, alpha state back. But A dagger acting on it does not remain into alpha state. Alpha is eigenstate of A operator only. A dagger and A do not commute, so therefore it is not eigenstate of A dagger operator. So therefore it is not a number eigenstate. Still, we can find out. Sorry, still we can find out what is the effective number density in that. This is not eigendensity. This is effective number state. And once we have effective description, we can find out what is the normal order Hamiltonian as well, which was, remember, apart from a divergent piece, there was a number operator with extra omega k multiplication. So you do that, you will get that the effective number density times omega k integrated over d3k is going to tell you what is your total Hamiltonian above the vacuum divergent piece. So this is the energy content. This is normal order thing is comparing its energy above the vacuum state. So this is above the vacuum state. If you put all alphas to 0, then that means you are talking about vacuum state. There is normal ordered Hamiltonian is 0. That means energy is exactly like the divergent piece which comes through vacuum. Okay. So this is the broader structure of the coherent state, which would be handy for us if when we discuss interaction of atoms with classical light. The classical light, many of the times, not most of the times, can be mimicked by a coherent state up to a vacuum, as we have seen. So if you want to extract out hidden quantum features in classical light, we can use this description of coherent light and try to see whatever the reminiscent quantum effects are there, what they are supposed to do to a system. That we will see when atom light interaction we discuss in more detail. Okay, so for coherent state, I stop the discussion. There is enough literature available on various other properties of coherent state, which we will not be going into that detail, but we have just constructed things and ideas which will be useful for us in our later part. So I stop over here for this discussion session.